In section 10.3, we're going to apply the same rules of what we did in 10.2, but this time we're going to be working with the mean instead of proportions. So we still have a huge 6-step process, just like we did for the last section. And again, that's in your inferential statistics cheat sheet, so just have that on hand. Notice in this case, simple random sampling is needed, independence is needed, just like before, but here we only need n to be larger than 30. That's not the case for proportions. For proportions, you need to have it so that n times p times 1 minus p, oops, right there, is greater than 10, okay? But for means, we only need n to be larger than 30. That's what we learned in section 8.1, that as long as it was larger than 30, then it would be basically normal. We have our options for our hypotheses. Notice that the null hypothesis always has equals, just like before. And then we can have two-tailed, left-tailed, right-tailed, depending on what our alternative claim is. We have our alpha level, our test statistic values right there, right, which should look a bit familiar, but you take your mean minus your standard, or minus your population mean, assumed population mean, and you divide it by your standard error, s over the square root of n. Now, we have the classical approach and the p-value approach. And just like before, the classical approach is actually kind of the harder one to do because you're going to need the table, or you're going to need a computer program to find the critical values. P-value is easier because everything just gets done for you with technology, and then you go from there. Okay? So we have the United States Mint, according to the United States Mint, quarters weigh 5.72 grams. A researcher is interested in determining whether the new state quarters have a weight that is different than the old value of 5.72. He randomly selects 18 state quarters, weighs them, and obtains the following data. So we're going to have to type those into Excel or StatCrunch. So first thing we need to do is we need to conduct, judging from the thoughts below, is it possible to make a hypothesis test for this data? And why do we even need this in the first place? So I want you to notice that nowhere in here does it say that this comes from a normally distributed population. So our data was from a random sample, so that's good. But the graphs are given because n was less than 30, and we weren't informed ahead of time that the data was normally distributed. So we draw the graphs to show us that the data is normal with no outliers. Therefore, we can conduct a hypothesis test. Again, that's all up here with these requirements of a test. It has to be from a simple random sample. It has to be either a large sample, right, bigger than 30, or it has to be normally distributed, or both, right? You can have a large sample from a normally distributed population, that's fine. And then it has to be independent, which we assume one quarter doesn't really have an effect on the next quarter, so that's kind of a given in this particular instance. Okay? So right here, oops, they give us this picture to prove us the normal thing. Because n is smaller than 30, we need to show that it's normally distributed. All right, so yes, we can make a hypothesis test right here. We can conduct a hypothesis test because this data is normal, that's the top graph, with no outliers, that's the bottom graph. Cool, we're all set there. All right, at the 0.05 level of significance, is there evidence to conclude that state quarters have a different weight than 5.72 grams? Use the classical method. All right, step 1, you've got to make hypotheses. So for us, we assume that the weight is 5.72 unless we can prove it's not 5.72, right? They said different, so that's why we use the not equal to. Step 2, we need a level of significance. They gave it to us. It's alpha equals 0.05, so we go with 0.05. Step 3, we need a test statistic. So that's 5.702. Now, where is that coming from? Well, I have the penny weights, or these are quarter weights. Quarter weights right here. So how could we get all that info out of it? So this is 10.3 example 1. Well, you could just get Excel to find the average for you. Average. Right there. And we are also going to need the standard deviation, so you might as well find it. STDEV.S of that data set. So that's one way you could do it. You can find it that way. You could also take those same numbers and put them into StatCrunch, which I can do right here. There we go. Hold on one second. Let me make that bigger so you can see it. Oh, it occurs to me you might want to know how to do this. So go to Edit, go to fonts, and you can make it so that you've got size 20. You can also make your result text larger too if you're interested in all of it. Say update font. There you go. Now you can see it a little bit better. And if you want to make the column wider, just go to columns, widths, click auto size. That's what I do, and say OK. And there it is. Okay, so there they are. And you could run stats, summary statistics on that column with no trouble. And there you can see your means 5.702, your standard deviations 0.0497. Yeah, 0.0497, excuse me. Okay, so you find those values, you put them in here over the square root of 18, because that's how many were in your sample, the number in your sample, and you find negative 1.519. You can do it by hand with a calculator, or you can use StatCrunch to do it. I'll show you that a little bit later. All right, then your critical values. Now this is the rough part, but you've got to use either the t-table or technology to find it. So you draw a picture, because they have a picture drawn in the classical method for two-tailed. Right over here, that's what you're drawing. Now the two tails together make your alpha, right? So alpha was 0.05. So that means alpha over 2 is 0.025. So over here on the left, you've got 0.025, and over on the right, you've got 0.025. All right, so then these statistics are these critical values are the t alpha over 2 and the negative t alpha over 2. So if you find one, you've found the other. How could we find those? Well, we've done this before, but let me just remind you that alpha over 2 is equal to 0.025. So, oops, let me make this larger so you can see it. Okay, so then the critical value would be equal to t dot inverse, INV, 0.025, comma, you need your degrees of freedom, which was 17, because remember, n was 18, so your degrees of freedom is 17. Matter of fact, I'm going to make a note of that somewhere. Hold on one second. There we go. Now I made a note of it for us all so we can all spot it. All right, so that we had degrees of freedom equal to 17, n minus 1, 18 minus 1 is 17. Alpha over 2 is 0.025. We're doing the over 2 thing because this is a two-tailed test. If it was a one-tailed test, let me scroll down, you can see you just use the whole alpha, right? But when it's two-tailed, you got to use alpha over 2, just like we did with confidence intervals. All right, so then, let me see. So how do we get that plus or minus? So you can see I got it right there, 2.1. So that's from Excel. You also have the option of using the table, which we've run into right here. You say, okay, I want 0.025 column. You go down to 17 degrees of freedom, and there it is, 2.110. So you could get it from the table, which you'll have available to you during the final exam and during your other exams. And if I were you at home, I would just print one off, or so you can have it next to you at all times. That way you can use it. All right, so there we go. We know how to find this either with technology or with the t-table. And I just wanted to mention real quick, I just flipped up here, but I put that in there. You can either use technology, StatCrunch will find it as well, Excel will find it, or the t-table. One way or another, you can get it. All right, then you're going to compare that critical value with your test statistic. Okay, so our critical value was 2.11. Our test statistic was negative 1.59. So that's not in the critical region, not in this gray area over here. It's kind of here at 1.5. So therefore, we are not going to reject the null hypothesis, right? A test statistic of 1.5, which is right about there, is not in that gray critical region. So there is not sufficient evidence to support the claim that the new state quarters are different in weight than the old state quarters, because our negative 1.519 is not lower than that negative 2.109, or 2.110, I guess, nor is it higher than positive 2.110. You have to be over on the high side on the right, bigger than 2.110, or lower than negative 2.110, and we are neither of those things. So we are not going to reject the null hypothesis. And real quick, look back at the two-tailed hypothesis thing. That's what it says. If your test statistic is lower than the negative one or higher than the positive one, you reject. But we did not have that. Scrolling down. What about redoing that with the p-value method? Okay, cool. So let's use StatCrunch, shall we? StatCrunch is going to be way simpler on us. Only highlight the quarters. Don't take all this stuff. This was the mean, by the way. This was the standard deviation. I might as well label those. Okay, so in here we've got our quarter weights. I'm going to take these into StatCrunch right here. Oops, I already have them. Okay, so we go to Stat. Now in 10.2 we did proportions because we were working with proportions. This particular section we're working with t-statistics. We want one sample. By the way, 2 sample and paired, those are coming in chapter 11. So keep an eye out for those. But for right now in chapter 10 we're working with 1 sample. Now we actually have data for this problem rather than a summary. Although we could use a summary as well because we've already used Excel to find those summary statistics. But if you didn't want to do that and you just want to type in these numbers, then use t-statistic 1 sample with data. It says select the column where your data is. So for us it's quarter weight, so I click on that. It puts it over on the right side. Say next. Now what's your null mean? Our null mean was not 0. If you look at our null hypothesis, it was 5.72. So you have to tell it 5.72. It was a not equal to test, so we leave it on the not equal to sign and click calculate. And there it is. I'm going to copy and paste right into Excel. This is so much easier than anything else. Okay, and you can see there's your test statistic right there. You don't even need to use a calculator for it if you have a computer up. Of course, if you don't have a computer up, then you'll have to use your calculator to find that number. It even tells us the sample mean. Heck, we didn't even have to go to all this trouble down here finding the sample mean because it finds us for us right there. It did not give the standard deviation, interestingly. It only gives the standard error. But hey, you know, don't forget what that is. That standard error is s over the square root of n. Square root of n. So it's kind of actually giving us more than we asked, more than we bargained for. That's the entire denominator on that test statistic. When you go in here, s over the square root of n, it's basically giving us that 0.049 over the square root of 18 already, and telling us that it's 0.0117 right there. So it's giving you all the pieces you need to run the test. And you can see the p-value is 0.1471. All right, so how do we do that when we do it by hand? Well, you can't do the p-value portion of it by hand. You have to get it from technology, which doesn't mean you won't be getting it on a test, because I can just give you this output. I can say, here's the output, go to town, right? Answer all the questions, run the test. So I've done the calculation part, but you've got to do everything else. And what you do is you draw a picture. Let me scroll back a little bit. You draw this picture, and yes, you still have to do this. Draw it by hand. It looks like a normal curve, but it's not. It's a t-curve with degrees of freedom of 17. You put down your test statistics, which is 1.52 and negative 1.52, not your critical values. That's the classical method, where you put in your t alpha and negative t alpha over 2. But in the in the p-value method, you just put down t0 and negative t0, which is honestly a lot easier. The p-value method is way easier. And then this p-value, 0.147, is both those two tails put together. Automatically given, automatically added up for you. Notice again, we do not reject the null hypothesis. We didn't reject it up here with the classical method, so we're not going to reject it here with the p-value method. This time, though, it's because the p-value is larger, 0.1471 is larger than alpha equals 0.05. Okay, so again, reiterating, if you don't reject one method, you won't reject the other method. The p-value method is the one the calculators and computers give you, so you're going to see it more often, and it's actually a lot easier because all you do is look and see if that p-value is less than alpha. Okay, we're done with this problem. I'll meet you back here for reading computer output in the next problem.